to the place where we finished yesterday? Okay, so the last thing we said yesterday was a recap on the thermal motion in liquid, and I started introducing the concept of caging at intermediate times when you have a liquid that is going slower. And it might go slower because it has a higher density, or it might go slower because it has a lower temperature, or both things that are also in between connected. But before going to a glassy behavior, which is the behavior that we want to learn about to understand about the studies on water that I will present to you, I would like to show you in details this density correlator we did talk about yesterday. How do they behave for a very simple liquid? So a simple liquid, like could be water, but at, for example, in the case of water, because it depends on freezing temperature, at ambient temperature. So water at ambient temperature has this behavior that I am describing in the first part of this lesson today, which is the Brownian regime. Always remember that at the beginning you have a ballistic motion, okay? So after the ballistic motion, then you have a Brownian motion, which is the random walk of the drunk person. You, if you are graduated in physics or you are undergrad, you might have seen these Brownian models in other courses and treated in slightly different way because it's a random walk. So you can have several models that take you to the same results. So, but looking at the history, the motion due to random collision were observed at the beginning by a botanist, Dr. Brown, in 1827, in a study on pollen suspended on water. So now, this at the beginning was a model for a particle suspended in another one, so a colloid, pollen, but it works also for pure water. The single molecule of water is also a random walker. It's only that they observed it for a macroscopic property particle because they had no microscopes, could not see so small as such a small particle as water. But for this reason, we call it a Brownian motion. And are particles subject to frequent collisions, but are random collisions, so like the drunk, and when I emerge from the collision, I forget what I was doing before the collision, okay? So I have no memory, so I have no memory effect. No memory of what happened before the collision. Typical of the drunk people. I take you home, no, I take you home, no, I go here, no, I go there. Okay, this phenomenon was studied extensively by Einstein. You know that Albert Einstein, or you might know that Albert Einstein in 1905 made 5 seminal most important papers. I don't know what happens to that. The brain was functioning particularly well that year. One of these papers is the special relativity, not the general, the special, but a milestone in his work. And another one was on the Brownian diffusion, one of the 5 papers. There is also a little booklet of the original 5 papers. If you don't have it at home and you're a physicist, you might want to buy it and read those 5 papers. But or at least this one connected to condensed matter. Okay, so it was studied in one of his famous work in 1905, one of the 5 famous. Einstein considered a colloidal particle like the pollen suspended in a background fluid and of medium composed of small molecules, and he connected the Brownian motion to the diffusive process of the colloid. We follow here the approach of Langevin. If you have a particle that moves in a medium because of collision, you can, first of all, decouple the 3 direction in space, as you did in physics 1 always, okay? So we now look only at one of the 3 directions, the other 2 will have the same equation. And the fact, if the particle is large enough, then the medium will have only an effect of a friction, of slowing down, like a viscosity, okay? So if it's a friction term, as you might remember from even from physics 1, you have to, the equation of motion, the differential equation of motion has a term which is proportional to the derivative of the position with a coefficient. The solution for the velocity, it's an exponential decay of in time, it's an exponential decay of the velocity that the particle had at the time 0 because of this viscous effect of the other particle. It's a very simple model. Langevin introduced also a random force. The random force represents the collisions. So you have this friction, but also collisions. So Langevin introduces the random forces, and we expect the motion to be random. So the average, thermal average of x must be 0, while x squared is different from 0. And these are time average. And from the random force, analogously, since it's random, the average between the random force and x must be 0, because this is a random variable. So if we multiply by x, now it's a bit of tricks, a differential equation here. So this is a very easy passage from here to here. And let's remember also this fact. And then we note that the second derivative with respect to time of the position, time the position, is also the derivative with respect of time of x of the first derivative and the position, minus the first derivative square. If we note that this is the very easy thing that you can deduce from this derivative, then we can make the substitution in the previous equation, which I'm taking you to the mind here. And we can write that the derivative of this is equal to this. This is equivalent of the equation that we just left. Then we can perform an average over time, and we use the equipartition theorem, which is a famous theorem of statistical mechanics, who connects to kBt the kinetic energy of the particle. This also is something that you have seen for the first time in Physics 1, in the basic courses of physics. Also for those who did not do physics, you must have seen it. Physics, I mean, as a subject, complete subject, you must have seen in Physics 1. And then for those who did the statistical mechanics, basic statistical mechanics, this is one of the fundamental theorem. Using the equipartition theorem, we substitute this here, and we find the equation comes to this expression. The solution of this differential equation, if we eliminate the derivative over time, is this one, where now we have that the average of x dot x is kBt over mc, which was the friction coefficient, plus a constant, which is due to the integration, e to the minus xi t. So we have to determine now the value of this constant. We use the initial condition that the left-hand side of the equation that we just saw is 0 at t equal to 0. This is 0 at t equal to 0. And this determines the value of A. It's a simple passage that I leave to you. So this is the equation that we are left with now. So we have x dot x averaged is equal to kBt over m psi, 1 minus e to the minus psi t. We manipulate, and remember that we can introduce the derivative here. Still can introduce the trick of the derivatives. We just need to add a 2 here. So these are equivalent expressions. So that finally we get x squared averaged. So a quantity we are interested to, which is the mean square displacement in 3 dimensions. This is the mean square displacement in 1 dimension. And we find that the mean square displacement is equal to 2kbt over m psi t plus 1 over psi e to the minus psi t minus 1 over psi. And it's easy to see that the limit for t that goes infinity of this quantity is proportional to the time, okay? It's proportional to the time, and the proportionality factor is, we will see in a while, it's the diffusion coefficient. So this result here is valid in all the directions, as I told you. So we are thinking only along x, but the other two are equivalent. So the mean square displacement is 6kbt over mc times t. Okay. It is usual to introduce, as Einstein did, the diffusion coefficient kbt over mc to get finally the Einstein relation, which is valid for the mean square displacement at long time. So if you're working in 3 dimensions, r square of t is going to be 6 dt. If you work in 2 dimensions, r square t is going to be 4 dt. If you work in 1 dimension, x squared t is going to be 2 dt. Okay, so remember that the number here depends on the dimension, but d is always the same. Okay, as always, this expression. Okay. For t that goes to 0, out of the expression, the general expression out of the general expression, this one here, that we found, for t that goes to 0, we find that we get the other limit, which is the ballistic regime. So 3 kb t over m is equal to times t squared is the behavior of the mean square displacement. So the ballistic regime has a t squared behavior in mean square displacement, while the diffusive regime has a t behavior. So you will have a mean square displacement if you plot it log-log. For the ballistic part, you will have a slope which is 2. For the diffusion part, log-log, you will have a slope which is should be 1, but it's d, so it's proportional, it's d. The slope is d, okay? So you will have a change of slope. So for a normal fluid, behaves Brownianly when you measure, and it has been done experimentally a huge amount of time, and this result is confirmed also for water. You first have the slope 2 in the log, if you plot the mean square displacement log-log, okay? You have the slope 2, and then you have the slope d. And so you can measure the diffusion coefficient out of experiments or out of simulations. Okay, so a short time, in fact, you have t squared because the friction coefficient does not appear. So the collision still do not affect the motion. The particle moves as a free particle. Therefore, this result is equivalent to the Newtonian motion of a free particle. For a long time, the Brownian limit is due to the fact that the particle has a lot of collision, and then the motion is completely random, and this leads, through the passage that we just saw together, to a mean square displacement that is proportional to time. And, as I just said, the proportionality is the famous diffusion coefficient you have heard about so many times. Okay? Now we will have to keep in mind this, that when we study a liquid, very often the very long time regime will be diffusive. When the fluid becomes complicated, we also have, on the other hand, sub-diffusive behavior, also asymptotically, okay? So many liquids asymptotically always go Brownian, although between these two slopes something else will happen, and we will see what happens when we go to the slow dynamics. But in some other case, when we have complicated molecules and the motion becomes very, complicated and tricky, then you might have also a subdiffusive behavior or a super diffusive behavior. So subdiffusing means that you have a lower slope. Super diffusive means that you have a higher slope, but you're not ballistic. But you have a slope, for example, higher than 1.5 you could have, or you could have a slope lower than 1, like 0.7. So subdiffusive, super diffusive. But the benchmark is always this, the diffusive, which is typical of the very simple movement of a particle. Okay, so now let's look at the, one thing that I want you to understand is this. Mean square displacement is the mean square displacement is an important quantity because it's practically telling the same story as the density-density correlation function. I mean, mean square displacement, self-intermediate scattering function, dynamic structure factor, they all tell the story of the Van Hove correlation function, of the density-density correlation function. And so we will see through this correlation always the same dynamics. But looking at one or the other, you can get a bit more of insights, but of the same dynamics. So for example, what is the connection between the mean square displacement and the Van Hove correlation function? Well, if we calculate the second moment of the Van Hove self-correlation function, in physics, moments are, in mathematics also, moments are defined as the second is the integral in all the space of the function times r squared. And then the third moment would be r cubed, and so on. So if you look at the second moment, and you perform the calculations here, there is some manipulation, you see that the second moment of the self-intermediate scattering function is the mean square displacement, okay? So the mean square displacement is directly connected to the self-intermediate, to the Van Hove self-correlation function. So this function here and this function here are two ways of representing the same dynamics, okay? So that Brownian diffusion we were discussing will be seen also if the liquid is simple here on the G self, on the Van Hove self-correlation function. And will be seen, of course, also in the intermediate scattering function and also in the dynamic structure factor, which were one, the Fourier transform of the other, as you might remember. Okay, we are talking about the self here that has appeared, as you can see, because this kind of motion, the random walker, is not a motion of correlation between the particles. There is no correlation. It's only the particle with itself. So we are talking only about the self-intermediate scattering function. Okay, so let's see, now that we see how R square is behaving, let's look at how, for example, in the limit of dilute gas, so when we have the dilute gas is when we have at the beginning in the mean square displacement the ballistic diffusion, what is the behavior of the self-intermediate scattering function so for a system of non-interacting particles. So when I tell you that I'm looking at this limit, this means that this behavior that I'm going to find for the self-intermediate scattering function now will be the behavior of the correlators, for example, of water, at the very beginning of time when they are still ballistic. When they are still ballistic, they behave like an ideal gas, okay? So no correlation. Okay, so let's look at the behavior of the self-intermediate scattering function. This is the definition that we gave yesterday. This, as you might remember, is the Fourier transform of the delta, so of the density correlation. So from the motion of a particle, if we have a particle that is moving and there is no force applied to it, from physics 1, this is the behavior of the particle, okay? We have, since we have this K times R, which is Vt, because we have no force applied to it, the self-intermediate scattering function will be the thermal average to e to the minus ik, the wave vector, time Vt. Okay, but the velocity, what shall I use doing the so I see I have to go, let's come back to this basic statistical mechanics. I have to do, for those who are less familiar, I have to do with it. I have to do a thermal average. I have a velocity. As I told you yesterday, I have to use the probability distribution of velocity of that temperature. So what is the probability, the distribution function of velocity of a gas of non-interacting particle of mass m and temperature T? Okay, if you studied it already, I just remind you that it's the Maxwell-Boltzmann distribution. It's a demonstration that it could be done. I could have even done it here, but otherwise I cannot do it here, otherwise the lesson becomes too long, but it's that one. So if you have seen it already, let me remind it to you, okay? So this is the distribution function of the velocity at a certain temperature. So at a certain temperature, you will have the maximum probability to have a certain velocity, which is related to the velocity of a particle that has the energy of the temperature of the system, of the average temperature in the system. And then, of course, all the other velocity will become less and less likely. But when I want to make an integral, I have to weigh them with their probability, because there is also a little probability that some particle will go very slow and some other will go very fast. But on the average, they will go with average velocity that is the temperature of the system, and they will take all the configuration compatible with this distribution in their phase space. Okay, so this is the average. So I take the expression of F self that I have to average, and I weigh it with the distribution function. Then I use the fact that this integral in the x direction is equal to this with the square of pi. This is a known integral. We get a Gaussian for F self of KT. So we will have this, so F self of KT is a function, you will see it at the end of this presentation here on the Brownian regime. It's a function that decays, okay? Because at the beginning, I am the particle who is at t equal to 0, r equal to 0, and of course I am correlated with my position at the most. Since it's normalized to 1, I will start from 1. So this is a function that always starts from 1, and then it starts decaying, okay? What is telling me this is that in the limit of Dirichlet gas, so until I don't feel the potential of the other particle, I will decay as a Gaussian. Then I will start feeling the potential of the other particle, and we will see how it changes, okay? So mean square displacement has a slope 2, at the beginning, in the log-log scale, and the f of qt is a Gaussian in time, okay? And you will see the picture at the end, so you will frame all that I'm saying now better. So it's a Gaussian. From it, we obtain the self-intermediate scattering function, which is also a Gaussian in omega, okay? But this is still the dilute gas, or for a liquid, the short time behavior. Okay. Also the Volkov correlation function, which we can obtain with another Fourier transform that I leave to you, it's a Gaussian, as you can see, with R square. So for simple liquid at normal temperature, and also for water, if we look at the mean square displacement, we find that goes from ballistic to Brownian. Here I plotted it in a linear scale. If it was a log-log scale, it would have been linear and linear, okay? Slope 2, slope 1. This is still, and you will see that log-log scale in a while. But now, for now, I use the linear here. Ballistic and Brownian, okay? Very well. So you will see this in the results of molecular dynamic simulations for water that I will point to you when we arrive to it. Okay, let's look at the hydrodynamic limit now. We already did talk on the hydrodynamic limit, but let me do a recap for you. Okay, in a dense fluid, we have collision with the relaxation time that goes from 10 to the 13 to 10 to the minus 13 to 10 to the minus 10 second. And the mean free path among the collision is equal to V times this relaxation time with the velocity that is always connected to kBt, as you know from the equipartition theorem. So if we now consider a wave vector, a perturbation of wave vector k and frequency omega that travels the medium, we are in the hydrodynamic limit if this perturbation is such as omega times tau is much smaller than 1, and k, the wave vector, times L, where L is the mean free path, is much smaller than 1. So if we are in this region, then we are in the hydrodynamic limit. Then we can use, consider the fluid as a continuum, and for diffusion, we can use the famous, in liquid state, Fick law. Okay, I don't know whether you heard of Fick law already or not, but Fick law is an empirical law, so nothing to understand. It describes the diffusion of a fluid, hypothesizing and then confirming with the experiments that the particle current, which is this J, depends linearly on the gradient of the density, okay? So where particles tend to have a uniform density. So if the density is high, the particle goes lower. If the density is low, the particle goes faster in order to restore the uniform density. And D is the diffusion coefficient that here is the same as Einstein's one, but here, as you see, is introduced as a phenomenological parameter in this Fick law. Okay, so, but since we are in continuous fluid, then we must have valid also the continuity equation. The continuity equation is an equation that you must have seen several times in physics, for sure in physics 1, also in physics 2, also the continuity equation of the current, no? If nothing is destroyed, when someone gets in, someone else has to get out. I mean, if someone is, we are not destroyed. If someone is missing from this room, it means that someone must have gone out. If we are more, someone must have get in. It's only this, the continuity equation. Okay, so they're all similar. So it's so the d in dt of rho of the density is equal to the gradient of the current. So if the density, so our density is changing in time, it means that there must be a current of people coming in or out from this room. This is the same for the particle of a fluid or for a continuous fluid. This is the continuity equation. The rate of change of our density here depends on number of people going in and out. This equation is valid only if we are not destroyed. If in this room someone all of a sudden disappears, then the continuity equation is not valid. You know? Why I'm saying that? Because there are various cases in physics in which the number of particles is not conserved. And if it is not, then you don't have the continuity equation which is valid. But if it's conserved, then it is. Okay, so combining the two, we obtain combining with the Fick law, we obtain that the derivative of the density is equal to d, nabla squared, the rho s of RT. And in K space, so we passed in the K space this differential equation, rho self will be OKT, and this becomes dk square rho self, and the solution is this one. So rho self of kt is equal to the value that you had at t equal to 0, e to the minus dk square t. So we see that it has an exponential decay. So you remember that in the free particle case, we had a Gaussian decay, and now we got an exponential decay. So as the mean square displacement is going from slope 2 to slope 1, correspondingly, the f of qt is going from a Gaussian to an exponential decay, okay? The exponential decay here is an exponential decay of the type e minus t, and of course this is adimensional, so this must be the inverse of a time, okay? So I define 1 over dk square as the relaxation time of my system. So in the hydrodynamic limit, we have this exponential decay, as I just say, and we have that tau is equal to 1 over d q squared. In fact, if you are familiar with this phenomenology that I'm describing, phenomenology and theory that I'm describing, very often experimental paper talk about a violation of this law, because when we are in a slowing down, we are slowing down the liquid, this law is violated in the intermediate time, of course, because we have other phenomena. This is also a way to see that you have other intermediate phenomena in a liquid if you get a violation of this law. Because you can measure tau, for example, from neutron scattering, you can measure the diffusion coefficient, and then you try to calculate the tau dq square, because when you do the measurement, you do it a certain wave vector, okay? So you calculate a dq square, and if it's not 1, if it deviates from 1, then you know something else is going on, it's not Brownian, okay? The diffusion. Okay, and you don't have this hydrodynamic limit. From this, we get the Ivanov self-correlation function that is equal to this a Gaussian in space, okay? So the Ivanov is a Gaussian also. And so we have exponential the FSF, Gaussian the Ivanov with these values, and the Fourier transform in time of the dynamical structure factor is this one, the dynamical structure factor, self-dynamical structure factor. This function here is a Lorentzian function, so it's like a bell, similar to a Gaussian, but it's a Lorentzian, so it's not a Gaussian. And the full width half maximum is 2dk squared, okay? This is important always when we want to relate to experiments, because this is a quantity that the experiment measures. In the neutron scattering, you measure for water the self of k omega. You remember I told you that hydrogen has this huge cross-section incoherent. So we measure exactly this function. And so you measure it, and you get, once you clean your very dirty spectrum out of the cell contribution, of the multiple scattering, blah, blah, you are left with this very nice result that you can have directly the diffusion coefficient from the full width half, the full width half maximum. Okay, so to recap, what we learned so far, that a simple liquid has the 4 pi r squared G self, which is which as a function of time. Each of these curve is as a function of r, and each curve corresponds to a time, and the time is growing when the function becomes larger. Okay, we saw that these are Gaussian, and Gaussian also here. This is the log-log plot of r squared, and we pass from 2 to d in 3 dimensions, to 6D, sorry. I mean, this is if it's a 6 proportional to D. So this is 2 and this is proportional to D. And then this is the f of kt, which, as you might remember, was Gaussian at the beginning. And then simple exponential e to the minus t over tau, where tau is equal to 1 over dq squared. So we learned all these things. We learned how a simple liquid behaves with this density correlator we are interested in, okay? Now for us is the moment to start introducing the phenomena related to the glass transition. But we are already halfway, because in this phenomena, the beginning will be ballistic, the end, most of the time, will be Brownian, and there will be something in the middle. But I will also extract a diffusion coefficient, and I will also see the ballistic part, how it changes when I supercool, the slight change of the... This Gaussian here is associated with another faster relaxation time, so we can measure that fast relaxation time too as a function of temperature that goes down. Okay, so we learned this so far, but it's already halfway of where we want to go to understand deeply the correlators. So in the next part of this lesson, I don't know if I will end today or not, look at the phenomenology of the gas transition. Since I'm going to change topic a bit, I suggest a 10 minutes break now, and we recover in 10 minutes, okay? 10 minutes break. Do you have questions before the break regarding this part? Okay, we can do it also at the end, okay? 10 minutes break. As I say to my student, sharp. And in fact, usually I start my clock. When I give 10 minutes break, I start the clock. What? Marcia, can you call, because I don't see my presentation on Zoom now, but maybe
they make for the break?
I'm not sure. I'm not sure. Yeah. No, I can ask them. Where are them?
I go.
Okay. Because I don't see it here.
Not around, probably not all of them speak English.
Do you know if they will make it available online, the slides of presentation?
They are recording it, so I hope so. But in any case, I can send you the PDF, so I will send it to them so they can send it to you.
Oh, nice.
But since I have some misprint, maybe I correct the misprint, I prepare everything, and at the end I'll send it to you. But yes, some of the things that I treated are also in my book. But
Yes,
I'll give you the presentation, because the presentation is a full view altogether of this particular. The book treats a lot of Yeah. Thank you.
I think everybody's here.
Yes, I think so, but it's nice to hear that sound, which is the signature that we are beginning. Okay, so now I'm going to talk about the glassy dynamics, which is the part that I will focus the most on the rest of my lectures on water. But first of all, we will talk again for today on the glassy phenomenology. So this is the summary of this part, which I'm not sure I will finish today, but in any case, this is the summary of the next, what is going to arrive. So glassy phenomenology. There is one theory, which is the Mock coupling theory, that works quite well for simple liquids and surprisingly also for water, which has a structure, because it was originally formulated also only for simple monoatomic liquids. And I will show you the equation of Mock coupling. So deeper meaning will be more for the experts. For the other, you will more or less follow. It's if you are still undergrad or you're not in physics, it's all right. I mean, the rest of the lesson will be phenomenological, but we'll see some equation of Mock coupling, the basic equation of Mock coupling for those who can follow. Then we will talk about the phenomenology that Mock coupling predicts, which is the same phenomenology measured in experiment. So that part will be accessible for everybody, I hope. Then I will show you a typical example, which is also the first mixture with which the Mock coupling theory was tested ever, which is the very famous, for those who do simulation, Cobbe-Anderson binary mixture. It's a binary mixture of Lennard-Jones particles. Lennard-Jones is a simple potential. If you're not familiar with it, you will see it. And they had to do the mixture because Lennard-Jones makes the crystal. There's no way to supercool it at a certain point. And also they had to change the mixing rules of interacting, which usually we do with the averages, and these are called Lorentz-Berthelot mixing rule, and instead they had to change the parameters of mixing so that they could mix more. Otherwise they tended to make crystal also this one and separate. So they twisted a bit the parameter, made this Lennard-Jones, Cobbe-Anderson, Lennard-Jones binary mixture. I will show you, this is a work that I have done back in the days, in the past, that the Lennard-Jones, this glass transition phenomenology works also in confinement. And I will show you that this Mock coupling theory works until a certain temperature. And from that temperature below, you have to resort to other, let's say, theories, but that are more phenomenological. Because Mock coupling doesn't take it into account the effect. I mean, it has incorporated it, but it's not so popular, because it's a complicated mathematical theory, Mock coupling. So, and so below a certain threshold, we will have to go to another kind of theory phenomenology, which is the one that includes hopping processes and the study of inherent structure, which we'll see what they are. And tomorrow, for sure, even if I don't finish today, we will start talking about the glassy behavior of water anyway. So, supercooled liquid and glass transition. What is the connection? When we have a liquid, let me remind you, or tell you for the first time, that if we follow an equilibrium path, then we are going toward the crystal state. The crystal state is the only stable state for a liquid below the melting, okay? Can only be a crystal. But if I cool it very fast, for example, The liquid has no time to go to its stable state. So if you think about the potential energy, there will be only one very deep minimum, which is the crystal state, but there will be a lot of relative minima in which the fluid could get trapped. Because if I take, let us suppose that we are moving, all in this room, and I tell you that you have some equilibrium position, the crystal, and the equilibrium position are round circles in the room. We move, no? We start moving. At a certain point, I tell you, okay, go to the equilibrium, and you start moving toward the closest part where you have to stay, okay? You start moving, but while you move, I take off you the kinetic energy, so that while you move, you become slower, 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 and at a certain point, you cannot move any longer, and you freeze where you stay. So you are not a crystal, you are a frozen liquid, disordered liquid, frozen. Okay. This is the glass. When you have no kinetic energy left, is a glass. But in principle, okay, but about the glass transition temperature, and if it's 0 Kelvin or not, is still in discussion, we will talk about later. All these states in which I'm trying to move, I do some little movement, but the equilibrium position is far away, I will never reach it. These are metastable state, because the stable state is the crystal, okay? So equilibrium path, stable state, metastable state. If we take off kinetic energy from the liquid fast enough, we don't give the liquid time to go toward its equilibrium state. So we finish in a metastable frozen state. So from a liquid, this is the freezing temperature or melting temperature, you go down and you get into a region in which you either have a crystal or you have a supercooled liquid. And the supercooled liquid, when you cool down more and more, eventually become the glass at the glass transition temperature. So we will come again to the glass transition temperature, because experimentally, the glass transition temperature is defined as the temperature in which viscosity is equal to 10 to the 13 poise. Poise is the unity of measure of the viscosity in the international system. So that's TG. But there will be other way of marking a glass transition temperature. Theoretician works on the inherent structure, call it Kautzmann temperature, and it's not this one, this is experimental, it's lower. Why are we defining this one? Because it is important also to compare different glasses. Glasses are important, very important for industry, for a lot of applications. So I need to know whether my glass has a glass transition temperature higher than the one that you produced. So you need to put some standards. So experimentally, the glass transition temperature is the one in which the viscosity is 10 to the 13 poise. You can use the definition to compare different glasses, but theoretically, the glass transition temperature is not this one, because at this temperature, particle can still move a bit. Okay, can make some slight rearrangement, and in an infinite time, they are still ergodic. Okay, but it's still not a stable state. Okay. So what's the Vogel? Then there is viscosity experimentally follows a low temperature. So in the deep supercooled region, a law which is called Vogel-Fulker-Tamman law, which is that the viscosity is an exponential of B over T minus Tk. And this Tk is the Kautzmann temperature. So the temperature where the viscosity diverges. Viscosity diverges at the temperature in which the particle cannot move any longer. I'm going to my equilibrium position, I'm stuck in a minimum. For example, in a minimum, I need some fluctuation, thermal fluctuation to move again, but you're still continuing taking off kinetic energy from me. So I am heavier and heavier, I cannot move, okay? Heavier, ideally, because mass is not involved direct. So, you see, This is the Kautzmann temperature, this is the glass transition temperature. They're not the same, but this one is important because you need to set standards. Where Kautzmann temperature is, the theoretician is still discussing, the theoretician working in that particular more supercooled field. I work in the more in the mild, although I've done something for the inner structure. But anyway, they're discussing if it's at 0 Kelvin or can be at a finite temperature, the temperature in which the particle, except for quantum effect, don't move any longer, okay? Because otherwise, at TG, what happens is that particles are still, but can have some thermal fluctuation for which they can do little movement. I don't know whether you ever heard that the glass of the window, it's a silica, a CO2 mainly. That is a glass, okay? But it's below TG, but it's not at TK. So in a time which is above the life of the universe, so it's only a theoretical exercise, it will go to a crystal state because it can do little movements. But when you calculate the time is above the life of the universe, so what do we care? I mean, it's the Earth will be destroyed since a very long time, so ideally it's not at the Kautzmann temperature. I mean, that glass is not below the Kautzmann temperature, okay? So this is just because when you read about the phenomenology of glasses, so you know what we're talking about. Okay, let's see the temperature. So you understood from what I said that we have region of mild supercooling and region of strong supercooling. Mild supercooling, Mach coupling, not for all liquid, but for many simple liquids, it works. Strong supercooling, inner structure, activated process, and in the mild supercooling, the relaxation, dominant relaxation, a structural relaxation, large relaxation that imply large movement and caging. In the region of strong supercooling, we have hopping. So let me tell you this again. So we have a normal liquid, we go down, and we have a melting temperature, which is experimental. Then we have a region in which, for simple liquid, Mach coupling theory works. And the dynamics is mastered by the caging I described, the caging of the neighbors, okay? The caging that I described, and you will see also a picture, but let me do it now again. Let us suppose that I am, because it's always relative to where you sit, sitting on this particle, observing this particle. And we have neighbors, disordered neighbors around, okay? These neighbors form around me a potential cage, an energy cage that entraps me. So I start at T equal to 0, I start ballistic. But the temperature is going down, and the particle below temperature is, let's say, it's low enough, so the particles are very slow. So when I start moving, I feel this trapping of this cage of particle, and at intermediate times, I do rattling in the cage, and I cannot move. Eventually, this cage will move, this particle will move, and when they will move, let us suppose that I arrive here, I will be free to move and rotate. When I will be, so at the beginning, ballistic is the motion that we studied already. At the end, when I can move, is the part of Brownian that we saw today. But in the intermediate time, we have to put into the equation this caging, into the equation of motion. But then there is the other regime. What is the other regime? The other regime is that at a certain temperature, which is the temperature, the crossover temperature of the MCT, of the Mach coupling theories, all cages are frozen. But this temperature is above TG for many liquids. Not all of them. For all those liquids that can have hopping. What is hopping? You have, it's always me sitting here on my observation particle. Cages are frozen, okay? So I'm bound to rattle in this cage forever, okay? Because this will not change. But all of a sudden, because temperature is giving me thermal fluctuation, I get enough energy that I can jump outside the cage. I can overcome the potential barrier of my first neighbor. Where do I jump? I can jump in another empty space that is close. Let us suppose that here I have space enough to jump. If I get enough fluctuation, I jump here. This is a jump. So it's a hopping. So physicists call it hopping processes. Chemists call them, they are the same, they call them activated processes. Because you need an activation energy, which is given to the particle by the thermal fluctuation. When you have the activation energy, you hop and you go there. Okay, so the picture now starts getting more clear. So, below TC, when all cages are frozen, so let me tell you, this is a stable state. The crystal is the stable state below Tm. This is a metastable state, but it's still ergodic. The system stays here long enough to explore the whole phase space. When cages are frozen, in principle, ergodicity is lost. But hopping processes restore ergodicity. So it's the hopping process that restores ergodicity below TC. There is an extended version of MCT that includes hopping, but it's not so popular. And then we have the study of inherent structure. We will talk about what happens in this region, what we can do. Then we have a glass transition temperature, which is the one in which viscosity is 10 to the 13 plus. And then below TG, we have the glass. But if we want to treat it more theoretically, we can say that the glass is below the Kautzmann temperature, or it's below this T0, which is the Vogel-Fulker-Tammant temperature, which should coincide with the Kautzmann temperature, but someone says no. So I wrote them both. Here things become more or less clear in that region at the moment. They're studying it, but not me. Okay, so what is this Mach coupling theory? The Mach coupling theory is a way that Wolfgang Goetze and some of his collaborators, especially him, found out to introduce memory effects that were simulating the cage. Of course, introducing memory effect in the Langevin equation, which is the equation of motion of liquids, was not done by them as first. But then they found this way of introducing it in a way that you will see that was new, and that was working for liquid. At the beginning, Wolfgang, I knew him, he passed, unfortunately, but started to apply, he wanted to apply this Mach coupling theory to the conduction of electrons in wires. But it was sort of working, but not so appreciated. So it turned to liquids. And then liquid is working, and so it was very popular. He was a mathematical physicist. So this is the book, if you're interested, this is the book that he wrote soon after he retired. And it's very nice, but it's also a very physical mathematical book. But here I'm going to describe only the basic equation of the ideal version of Mach coupling theory. But there are many versions, and then you can introduce hopping. They have this version is for a single atom, but then you can have dumbbells. They worked on dumbbells, etc., etc. There are several extensions. There are several singularities that you can have. But we're not dealing with that because it has nothing to do with the phenomenology of water. So there are other phenomenology. Oh, let me tell you something. For colloids, for colloids usually there's no hopping. So for colloids, the glass transition temperature is the Moe coupling. For colloids, Moe coupling works very well until the end, okay? Because they're too big, they don't hop. Okay, in class, so let's look at the Moe coupling equations now. In the classical hydrodynamic equation of motion, for the density correlator, you have the damped harmonic oscillators. If you are familiar with the damped harmonic oscillator, I always tell to my students that you can do almost everything in physics with the forced damped harmonic oscillators. Many cases in which in physics, not only condensed matter physics, you use it, you also do the quantum treatment, and you do a lot of things. And this is not less than the other. So in classical hydrodynamics, the equation of motion is this, where phi is, for example, our density correlator can be. Okay, it can be our density correlator. Okay, and omega q is a constant time q, and it can be generalized to a and this is a hydrodynamic regime. Okay, so you have a fluid which has a friction. This can be generalized to a non-hydrodynamic regime if you introduce a memory kernel. So you see it's a retarded memory function that you put here, okay? Here in this part, you put this retarded memory function. And M of Q is gamma times delta, so the usual term to recover hydrodynamics, and then you have omega squared is mq of t. So you introduce this retard. Okay, so let's now look at the typical temporal evolution of a dynamical variable. So this is the typical temporal evolution of a dynamical variable. This is a formal equation, where L is the Liouville operator, okay? Where H is the Hamiltonian, and these are the Poisson parentheses, okay? If you are familiar with what I'm saying, very well. If you are not, don't worry, jump only this part of the equation of my lessons about Moe coupling, because otherwise a whole lesson on this with all the things that you might not know is too long. So the Liouville, the Poisson parenthesis is the equivalent of the commutator in quantum mechanics. Then we introduce also a projection operator, which is this one. And so the Moe coupling, it's the equation of motion with the projection operator becomes this one. So if we look at the first term, this one, the A al T times P of the right-hand side, with the projection operator that we defined, becomes like this. So it's e to I al T times this part normalized. Then I can introduce an omega, a function that is a part of this, like, and I will tell you, I will come back to omega, to the definition of omega in a while. But we have also this second term. The work on the second term is a bit more complicated. I have to introduce, this is something that when you calculate is often used as an expedient. We introduce a second operator that is done properly in order for me to arrive to where I want to arrive. So sometime when you invent it, you design it backwards, okay? So you introduce this operator O of t that has this relation to e to the I al t, And if you calculate e to the ILT O dot, you see that is equal to this part. So this is the expression of the operator as it comes with the integration. And then you have this part here, e to ILT I 1 minus P LA, which is exactly what we have here, the second term, apart from I, which is equal to this part here, where we have this integral and we have this f of the time. One part of this is in the integral, part of this is here, and it's the temporal dependence that you have here and here of this operator that is written like this. Let's now see how I define omega and f of t, because here we have an f of t. We had in the previous slide an omega, which comes from this. So let's write the final equation, the final generalized Langevin equation. And so far, I'm only introducing memory kernel in the Langevin equation, and it's not Moe coupling so far, okay? This is, as I told you, the Moe coupling theory is one way to doing the memory kernel. But the memory kernel theory is already there, okay? So the Langevin equation, the generalized Langevin equation become this one. With this memory kernel, you have omega, which we defined in the first slide. Then we have this expression, which is our random force. And then we have this m of t, which is our memory function. The memory function is what gives us the memory of the past. So you remember that I said that when you move in a liquid like a brown, and you do a Brownian motion, you have no memory of the past. And then for you is the friction, is not the only thing you have to introduce. And every time you hurt somebody, you have a collision, you forget your past. But of course, if we want a particle to rattle in the cage, then we have to remember the past. We have to remember that we are in a particular situation. Because if I changed every time, not remembering where I were, I will never remember. So it's like I was living somewhere else. But this rattling in the cage is something that needs the memory. So memory function gives the memory of the past. So now, let us suppose that we focus on density. So if we choose density and the current, so the movement of the particle, the current density, as my variable of this A of t, with rho k, which is our usual rho k, and the current density is a rho k times k dot p. This is the definition of the current density, okay, in the k space. Then I can write a correlation matrix which is A0, AT, so the density or velocity correlation matrix, which is done by 4 terms. This is rho, our f of qt, or f of k of t. This is j rho j, jj. And then let's remember the frequency. When I have this correlation matrix, I will have a frequency matrix that is different between all these, and is a 0, ik, and these other part for these two mixed terms, and 0 for jj. The memory kernel is 0, 0, 0, and then we have this part for the jj. And the memory function becomes this with rk equal to this value. Okay. So when and this for now it's it. So then now we need to see how we can explicitly put this m of t in the equation. Let me remind you, for justifying this behavior, let me remind you that we are thinking about the self-intermediate scattering function, so the density-density correlation function. And remind you that we saw that at t equal to 0 is a delta, and the t that goes to infinity goes to 0, the self, and its Fourier transform is the incoherent intermediate scattering function is this equation. With this in mind, we can write the Moog coupling theory for the self-intermediate scattering function. So the exact, so far we have introduced no approximation, okay? So this is a formal equation, but it's still valid until it remains formal. If I knew how to write exactly this m, that would be an exact equation. But I don't know what is the real m. Okay, so the equation for the intermediate scattering function is phi, which is our f, the twice derived with respect to time of kt equal to omega square phi kt plus the integral between 0 and t of the retarded memory kernel m of k t minus t prime, phi derived with respect to the time of k and t prime in the t prime equal to 0, where phi of kt actually is not exactly the self-intermediate scattering function, but is the self-intermediate scattering function divided by S of k, the static structure factor. I did not introduce the static structure factor because you knew already what it is, because Enrique already did talk very extensively about this. So it's divided by the static structure factor. And omega k squared is kbt over m, k squared over S of k. Okay. So the equation, as I was saying, is in principle exact, but not solvable. In order for us to solve it, we have to introduce approximations, and here we start with the Moog coupling theory. Oh, sorry. Today I did it right until now. Approximation. So, first of all, we substitute the random force with a projection on a special subspace. And then we separate the kernel in a short time part m0 of kt and a long time part m of kt. And then we factorize the kt as follows. M of kt is this one. And here is where we do the Moog coupling. You see the kt as a vertex. This vertex is written only with the S of k. This is a very important thing of the theory. In order for you to calculate the dynamics, so the dynamic correlator, in principle, you need as an input only the S of k, only the static, only where are the peaks of the S of k that can give you the hint, that can give you the position of this cage. Then you put the cage, you have a temperature, you do the movement, you don't need anything else to do the dynamics, okay? So the vertex is on S of k. Okay, then you start mixing the modes. But for those of you who are familiar with the Kawasaki Moog coupling theory, I don't know if there is some of you, Kawasaki Moog coupling theory is an alternative theory to explain second-order critical phenomena. So I don't know whether you studied them, if you did the cumulant expansion to find the second-order critical points or not, but you can use the Kawasaki theory, which is a Moog coupling theory. But in the case of Kawasaki, for critical phenomena, at the end, only one mode drives the transition. Here is completely different world. So this Moog coupling theory has nothing to do with the Kawasaki theory for critical phenomena. This is not a critical phenomena theory, okay? The glass transition is not a real transition, it's a kinetic transition, okay? It's not a thermodynamic transition. So although Kawasaki, if you knew that, was using Moog coupling theory, in that case, there was, at the end, when you go to the transition, only one mode. Here, you have a mix-up of mode that gives you this phenomenology that leads to the glass transition temperature, which is a kinetic transition, okay? Very well. So we have a factorization of this with this vertex that contain only S of k, and then you have the modes. So here's the vertex, for example, for these two modes. So these are approximations. So this is one particular approximation that I'm writing here. So our equation of motion becomes like this. and with m of kt, which now is which is this one, which I have written explicitly. I just wrote what the vertex is. Why is this vertex having this particular form? And this is rather complicated. You have to read the book of Wolfgang Goetze if you want to see all calculation. You have the reference of the book. And also he wrote, there is a Lesouche school in which he wrote also this calculation. Maybe that is shorter, but probably the book is more clear. So I advise the book, but there is also a Lesouche, an article on a Lesouche, very old Lesouche school. Okay, it's time is finished. It's only 2 minutes. So I know that it's I'm missing something, not very much, but I have to stop here. We will continue tomorrow, and also maybe if there is one quick question or two, otherwise we can leave the question for tomorrow. Tomorrow we can go back to this equation if you have questions. Okay. Yes. Quick question. Okay. Sorry. Quick questions. Say it again.
In this case, the random force is a color noise, and is it in accordance with the population distribution theory?
Yeah, it can be a color noise, but there are several versions of the theory. So it's in this ideal case, you mean? Huh? Can you talk louder, because I didn't listen to you. I couldn't listen. I extrapolated.
My question is, the random force is according with a color noise, because it's not a white noise.
If it's a colored noise,
Yes.
the force, yes, yes. Sure. Okay. If there are no other questions. In the hopping, there is an extension of the theory who takes care of the hopping always with this kernel, but it's not very popular. And you will see if you look at the book that it's I have to write some equations. But yes, there is. But it was not so popular. So because what is very popular of this theory at the very end of the day is that there is, you will see it in the next 2 slides, an idealized version that gives a precise prediction on density correlator that we can measure with the simulation and experiments without having to make calculation for the theory. So this made the theory very popular. Because it says you will see density correlator has to do like this, 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 this. So we do the simulation and we see that the behavior is that, or the measurements, and the experimentalists see that this behavior is that, and this made this theory very popular. Not because of all this calculation that very few people do, but because it was able to handle prediction for simulators and experimentalists. But Wolfgang was continuously trying to make more calculations when he saw that there was some specific need. For example, when we tested that for water, we were the first to test it for water. Back in the days, I was at MIT then. He came to visit us. He was very happy, but he was surprised because at the beginning it was only for monoatomic system. So we started to do the dumbbells because, okay, let me try at least for a dumbbell. And for the dumbbells, for example, it works and there is a formulation specific for the dumbbell. But the prediction of the idealized version, if you calculate the center of mass of water, it holds also for water. So he was very happy, but he was working. Then this thing of the hopping also was becoming a big issue. So I said, okay, then I add the hopping, and I added the hopping. But it's the ideal version of the theory that works in the mild supercooling that works the best. Okay. Okay, thank you. Thank you.